to our online lecture series for advanced transport phenomena. In today's lecture video, we are going to be moving away from talking about, at least for briefly, talking about mass transfer and heat transfer, and start talking about fluid flow or fluid dynamics. And we'll start with 1D fluid dynamics, move into 2D fluid dynamics, talk about stream functions, things like that. And so I'm probably going to break this video up into two parts. Part one is going to be somewhat of a review. We'll go over some example problems that hopefully you've seen before. Some of the things that will be new is we're going to talk about fluid dynamics in terms of our quote-unquote new language. That is the vector and tensor notation. And then in part two, we'll talk a bit about dimensionless groups that arise from fluid flow, as well as solve some two-dimensional fluid flow problems. And so I always like to start off this section of the course with a quote from Sir Isaac Newton, which says, "Resistance which arises from lack of slipperiness originating in a fluid, other things being equal, is proportional to the velocity by which the parts of the fluid are being separated from each other." And why do we care about Isaac Newton? Well, that's because hopefully the majority of the stuff that you focused on in your undergraduate fluid flow class were Newtonian fluids. So what is a Newtonian fluid? For us, we will define a Newtonian fluid as a fluid that is homogeneous, as well as a fluid that is isotropic. In general, a fluid is a material that deforms continuously when subjected to a shear stress. So a fluid is a material that deforms continuously when subjected to a shear stress. We can write the constitutive equation for a Newtonian fluid. And if you're wondering where we are in chapter 6 of Dean. So the constitutive equation for a Newtonian fluid in our new language tells us that the shear stress tensor equal to 2 times the viscosity times the rate of strain tensor minus 1/3 the divergence of the velocity multiplied by the Kronecker delta divergence of the velocity Kronecker delta. Let me rewrite that a bit of a different form. Okay, so let me label parts of this equation. We should all know that tau here represents our shear stress. This is uppercase gamma, I believe. That is our rate of strain tensor. Kappa here, lowercase kappa. That is our dilatational viscosity or bulk viscosity. And then we have our shear viscosity, which is probably what you are all most dealing with or most familiar with. So the effects of kappa on fluid dynamics are pretty hard to detect. So effects of kappa on fluid dynamics are hard to detect. And so it is believed that this bulk viscosity is much, much smaller than the shear viscosity for fluids. And so moving forward, we will always make the assumption that the bulk viscosity, or kappa, is equal to 0. If we make that simplification to our equation, we end up with the following constitutive equation for a Newtonian fluid. So again, this is for a Newtonian fluid. For an incompressible fluid, i.e. a fluid whose density does not change. So for us, that's typically liquids. Gases can act as incompressible fluids. It just depends on what type of temperature drop arise or what type of pressure drop arise that occurs inside the fluid. So always good to think incompressible. We're typically thinking about a liquid. Incompressible again means that our density is constant, and it also tells us that the divergence of the velocity is equal to 0. For an incompressible Newtonian fluid, we have the following equation. Given that the divergence of the velocity is equal to 0, that second term on the left-hand side of our constitutive equation drops away, and we're simply left with 2 times the shear viscosity times the rate of strain tensor. This can also be written as the shear viscosity times the gradient of the velocity plus the transpose of the gradient of the velocity. where the gradient of the velocity is equal to the rate of strain tensor plus a new term, which is the vorticity tensor. The rate of strain tensor gives me a measure of deformation. So a measure of the rate of deformation. And my vorticity tensor gives me a measure of the rate of rotation. That rate of strain tensor is a symmetric tensor. That vorticity tensor is an asymmetric tensor. I can expand and define both the rate of strain tensor and the vorticity tensor. So the rate of strain tensor 1/2 the gradient of the velocity plus the transpose of the gradient of the velocity. And my vorticity tensor is equal to 1/2 gradient of the velocity minus the transpose of the gradient of the velocity. There are two kinds of deformation that a fluid can undergo. The first of these is a deformation where we preserve the shape but not the volume. And so that would look like something, or that would look something like this. Okay, so we have preserved the shape but not the volume. In the second, we preserve the volume but not the shape. So that might look something like this. Okay, and we could have a pure rotation. I'm going to put a star by that because I'm not going to technically consider that a deformation. which might look something like that. Okay, so what does all this mean? Well, let's start with a one-dimensional fluid. So for a one-dimensional fluid, we will also assume rectangular coordinates. My constitutive equation tells me that the shear stress is equal to 2 times the viscosity multiplied by the rate of strain tensor. You are probably most familiar seeing this equation look something like this. Where this is oftentimes referred to as Newton's law of viscosity. My subscripts here. Second one is the easiest. The second one tells me the direction of flow. So if I were going to draw this problem, let's say I have fluid moving through a square duct. My coordinate system would look something like this. Well, let's be correct about this. Technically, they're equal to each other, but let's do that. Okay. So for our shear stress, the two subscripts. Second one is always the easiest. What is the direction of flow? The direction of flow is, in this case, in the x direction with how I've drawn it. The first subscript is the direction in which the shear stress is being applied, or the plane on which the shear stress is being applied. So I have fluid that is moving in the x direction and applying shear on the y plane above. That's what I have here. So I have my fluid velocity in the x direction, and it is changing as a function of y. Okay. Another equation that hopefully is a review for everyone is the Navier-Stokes Equation. For the Navier-Stokes Equation, we are assuming we have a fluid with a constant density and constant viscosity. Navier-Stokes Equation in our new language. So we have the material derivative on the left-hand side, and on the right-hand side we have negative gradient and pressure plus the divergence of the shear stress plus our gravity term. For the purposes of this class, I am going to use a somewhat cursive, lowercase cursive p to represent pressure. Okay, so Navier-Stokes equation. We're trying to derive that. Here, what I'm showing you is what is known as the Cauchy momentum equation. So how do we get from the Cauchy momentum equation to the Navier-Stokes equation? Well, we have our expression for shear stress. We need to take the divergence of that shear stress Now I can carry out the operation. So I have my shear stress, my shear viscosity. I have the Laplacian of the velocity divergence of the velocity. Okay. Now, if we are assuming a Newtonian fluid, which we are, we know that for a Newtonian fluid, the divergence of the velocity is 0. So we can come down here to our equation, cancel that term out, and we are simply left with the shear viscosity and the Laplacian of the velocity. I'm going to take that. I'm going to plug that back into my Cauchy momentum equation. Okay, so I end up with the following equation. This equation right here is my Navier-Stokes equation. You will oftentimes find this written in a slightly different form. Okay, and here, my fancy P, right, the gradient of my fancy P, I don't know exactly what that P is called. I'm going to call it a fancy P, where the gradient of that fancy P is equal to my gradient and pressure minus my gravity term. So I've simply combined my pressure gradient and my gravity term. This is oftentimes the preferred form because there isn't any directionality per se in this equation. With that Navier-Stokes equation, there is a accompanying continuity equation, and the continuity equation is simply that the divergence of my velocity is equal to 0. So continuity equation. And those two boxed-in equations right there are the starting point to many fluid problems that you will encounter and many fluid problems that we will solve in this course. Okay, so that was a bit of a re-review that was recast in terms, or not a re-review, a review of fluid dynamics that was recast in terms of this vector tensor notation. And we end up here with our two final equations, our Navier-Stokes equation in a condensed form, and our continuity equation. So let's use these equations to solve a couple fluid dynamics problems that you are all hopefully familiar with. So the first example is going to be flow in a parallel plate channel. This is referred to as Quasi Flow. Hopefully I didn't butcher that French name too bad. Quasi Flow. What I'm trying to pronounce is Quasi Flow. In this particular flow, we have two parallel plates. The distance between those two plates is 2h. We're going to assume that those two plates are stationary. Because those two plates are stationary, we have symmetry in our problem. And we will define our coordinate system like that. Let's make some assumptions. Right, the first thing we are going to assume is that we have an incompressible Newtonian fluid. We are also going to assume that we only have one-dimensional flow. That is, we have flow in the x direction where that velocity is a function of y. And we will also assume that we have steady flow. Okay, let's start with our Navier-Stokes equation. I'm going to expand the material derivative on the left-hand side. Okay, so we have the following equation, and we also know, based on our continuity equation, that the divergence of the velocity must be equal to 0. We can, of course, make some simplifications. We'll also go ahead and make the assumption there is no convection, so steady flow. That term goes away, no convection. The second term on the left-hand side goes away. So what we are left with is the following equation. And now I can write that in terms of x's and y's based on the fact that I have rectangular coordinates. So again, I am concerned about the velocity in the x direction and how it changes as a function of the y coordinate. So the left-hand side then becomes my shear viscosity, second derivative of the x component of the velocity with respect to y, and that is equal to d fancy p dx. As I move down in the x direction, I have some change in pressure. Remember, fluids flow from high pressure to low pressure. This is the governing equation for this particular scenario. I can also write my boundary conditions. I'm told that both plates are stationary. Therefore, I have symmetry in my system. That's why I've drawn the dotted line in the middle of the channel. I do not need to evaluate the entire channel due to the fact that I have symmetry. So at either plus or minus h, the velocity of my fluid is 0. Right, that is our no-slip boundary condition. The no-slip boundary condition tells me that whatever my adjacent surface is moving at, whatever velocity my adjacent surface is moving at, the water that is touching, the fluid that is touching that surface is moving at the same velocity. I'll say that again. The velocity at which the adjacent surface is moving dictates the velocity at which the fluid that is touching that surface is moving. So in this case, we have a stationary wall. Therefore, we have a stationary fluid at that boundary. We also have a symmetrical boundary condition in the center of the pipe. So this is our symmetry boundary condition. Hold on, give me a second. I need to find the second part of my notes. Okay, we're good. So governing equation, boundary conditions that go with that governing equation. Note, I mentioned something earlier. I think we were up here, and I was talking about the subscripts on tau. Technically, for rectangular coordinates, it's somewhat irrelevant how you write that, because tau xy is equal to tau yx. So, if you wrote this the other way, or if I had written this the other way, that's fine. Irrelevant, they're equal to each other. Just wanted to point that out. Okay, so now let's solve that governing equation and apply those boundary conditions. We are going to integrate twice. and apply boundary conditions. I'm not going to go through the math. This is supposed to be somewhat of a review. What I end up with is the velocity profile of my fluid. So the x component of the velocity as a function of y is equal to negative half the height of my channel squared 2 mu multiplied by the derivative of funky p with respect to x, 1 minus the ratio of y divided by half my channel thickness squared. So that is the velocity profile of the fluid when we have flow between two parallel plates. Again, I mentioned something about why this is oftentimes found with this funky p, because it allows us to derive our equation without thinking about directionality. At this point, we can think about directionality. What do I mean by that? If the channel is horizontal, then that derivative simplifies to simply the derivative of the pressure. For the horizontal channel, we do not have any gravity that's causing our fluid to flow. In the other case, if the channel is vertical, so these are the two extremes, that derivative is equal to negative rho g which we could also write as rho times the x component of the gravity. Okay. If I wanted to draw the velocity profile or the shear stress profile for this particular scenario, I can do that. So there's my two parallel plates. I have my 0 point for my shear stress, my 0 point for my velocity. Looking at the velocity profile, I see that it goes as y squared. I know that I have symmetry. So I'm going to end up with some parabolic-like velocity profile, where the maximum of that velocity is going to occur in the center line of the channel, and I will have no velocity or zero velocity at the stationary walls of the channel. In contrast, I could take the derivative of my velocity profile, multiply it by the shear stress, multiply it by the shear viscosity. That would give me my shear stress. Biggest thing to note is when I take the derivative, this now goes as simply a function of y. It becomes a linear equation. For me to have my maximum velocity in the center of the pipe, I need to have my lowest shear stress, and then I have my highest shear stress at the wall of the channel, where again those are straight lines. So that is my shear stress profile and my velocity profile for this particular scenario. If I wanted to calculate the mean velocity of the channel, I could do so using the following equation. So the mean velocity is going to be equal to 1 over h multiplied by the integral from 0 to h of the velocity profile with respect to y. The form of this should look familiar. This is the same form that we used to determine the mean temperature when we were solving the fin problem. So for this particular scenario, if I plug in my velocity profile, I integrate, evaluate at 0 and h, I end up with the following equation. Now that I have an expression for my mean velocity, I can substitute that back into my velocity profile. And I can put my velocity profile in terms of the mean velocity of the fluid. That is oftentimes more useful for us and as chemical engineers when we go out and we want to measure the velocity of a certain process stream. We're typically not measuring the velocity as a function of distance away from the wall of the pipe. Right? We're typically sticking in some flow meter and it's calculating some average velocity for us. So this becomes our velocity profile in terms of the average velocity of the fluid. Meaning if I know the average velocity, I can use this equation to tell me what the velocity is at a specific place in those parallel channels. I can also calculate a volumetric flow rate per unit width. I can do that with the following equation. Q, lowercase q is equal to 2 times the average velocity times half the channel height. And so for our particular scenario, that equals negative 2/3 h cubed over mu, and then the derivative of funky p with respect to x. All right. So what happens in the scenario where we have flow in a parallel plate channel, but the top plate moves at some velocity? So now we have a scenario where the bottom plate is stationary, but the top plate is being pulled with some velocity. Again, channel height 2h. Okay, the issue here is that the difference here between this problem and the last problem is that we do not have symmetry anymore. We don't have symmetry because one boundary is stationary and the other boundary is moving at some velocity. Therefore, our boundary conditions, we need to write them at both plus h and negative h. So the x component of the velocity at h is equal to the velocity of that wall. That's, again, our no-slip boundary condition. and then the x component at negative h is equal to 0, which again is a no-slip boundary condition. Okay, we can do the exact same thing we did before. We're going to integrate twice, use those boundary conditions to solve for our velocity profile. So integrate twice, apply boundary conditions, which allows us to solve for the constants in our velocity profile. When we do that, we end up with the following equation. Again, I'm not going to walk through the math. And so that becomes our final equation for the velocity profile, specifically for the x component of the velocity as a function of y. We can see that that solution is simply an addition or a summation, or it's additive between simple flow between parallel plates where neither plate is moving, and the condition where we are actually moving the top plate at a velocity. That is referred to as Quasi Flow. So what do those velocity profiles look like? So we already know what the velocity profile for our Quasi Flow. We will add to that our Quasi Flow. And what we end up with is a velocity profile that is slightly skewed towards the top of the channel. This is the velocity profile that is being described by that equation. So let me write these French words out just in case I am butchering the names. So we have Quasi Flow and Quasi Flow. Oftentimes, or more often than not, as chemical engineers, we are dealing with flow occurring in pipes. I don't want to be redundant, but just so you understand, when I say pipe, I mean a circular pipe. So if we had quasi flow in a circular pipe, the governing equation for that, assuming we have 1D flow, going to look something like that. Which we can solve, obtain a velocity profile for the z component of the velocity as a function of r. And you will see it takes a very similar form to the equation above for rectangular coordinates. Our characteristic length here is now r instead of h. We now have a 4 mu on the bottom. We still have our pressure, dynamic pressure. Driving force multiplied by 1 minus the ratio of r to the radius of the pipe squared. So hopefully you can see this equation for rectangular coordinates. My equation for flow in a circular pipe takes on an analogous form. I can also write the mean velocity, or write the expression for the mean velocity of the fluid. Now using that mean velocity, I can plug that back into my velocity profile. To get the following equation. And I can also write a volumetric flow rate. So this is simply a volumetric flow rate. This is not a volumetric flow rate per unit width. So here I'm using uppercase Q. And that is the expression for the volumetric flow rate. Again, when we are talking about fluid flow in a circular pipe. All right, we're almost done. I just want to quickly go through one last review example problem. In this example problem, we are going to have flow in an annulus. Try to get that as symmetrical as possible. That's good enough. Okay, so in this particular problem, what we have is we have our fluid on the outside of the inner pipe, but on the inside of the outer pipe. So again, our fluid, if I can write this word correctly, is on the outside of the inner pipe and on the inside of the outer pipe. In this case, the inner pipe is stationary and the outer pipe is rotating with an angular velocity of omega. So we have our r direction, theta direction. The radius of the large pipe is r, and the radius of the inner pipe is 1 minus epsilon r. Zoom in. All right, third time's a charm. R epsilon 1 minus. Okay. So this is a scenario, and like most fluid flow problems, our goal here is to derive the velocity profile of the fluid inside that annulus. We're going to make some assumptions. Assume incompressible, Newtonian. We're going to assume 1D flow. That is the theta component of the velocity. It's going to be a function of r. We will assume we have steady flow. And we will also assume that we don't have any contribution from the dynamic pressure. So we will again start with our Navier-Stokes equation and the continuity equation. We'll write those out in their full form and then simplify them. Okay, so Navier-Stokes, continuity equation, we have steady flow. That goes away. I keep forgetting to write this, but no convection. So the second term goes away. We are told we don't have any contribution from our dynamic pressure. So we are simply left with the equation of the viscosity times the Laplacian of the velocity is equal to 0. I can convert that to cylindrical coordinates, and I end up with the following equation. Okay, this is my governing equation for this scenario. I can now write my boundary conditions for the problem. Okay, so I have two no-slip boundary conditions. I know that the velocity at 1 minus epsilon r, or the surface of the inner pipe, is equal to 0. That inner pipe is stationary. And I also know that the velocity at r, or the outer pipe, is equal to the velocity of that outer pipe. So here is where many students in undergraduate make the mistake of simply writing omega. Here is the boundary condition. Omega is our angular velocity and has units of per second. We need this to be not an angular velocity and a linear velocity. To get that to be a linear velocity, we need to multiply by the radius of the pipe. That becomes our correct boundary condition, which again is a no-slip boundary condition. Integrate that equation twice, apply the boundary conditions, and we will end up with the following velocity profile for the theta component of the velocity as a function of r. Okay, and if I've done my math correctly, I should end up with the following expression for the velocity profile for the fluid inside that annulus. Okay, so that concludes, and I'll go ahead and put a line here, part 1 of the video, where we have focused on one-dimensional fluid flow. Hopefully the example problems that I went over were somewhat of a review. If they weren't, you should go back, work through those example problems, make sure you can get to the velocity profile that I showed for each problem, because in part 2, we are going to pick up talking about various flow regimes, dimensionless numbers that come from fluid flow, as well as starting to solve some two-dimensional fluid flow problems.